In the last classes, we discussed about CNNs and we discussed about the different ways to forward and backward propagate in CNN, and we talked about different functionalities of CNN when they are used, how can they be used, and we talked about convolution. Now, today we will discuss about the different case studies of CNN. So what that means is you have a convolution neural network, right? And now there are a lot of ways in which you can define or make different convolutions. You can add different activation functions, you can change the number of layers, you can change the number of kernels in each layer and everything. So the whole thing is it can keep changing. So what people have done is they have a competition which is known as ALexNet, if you remember. So ALexNet is basically a competition where people have to build more and more models, and they have to get better accuracy. So ALexNet is basically a classification problem and it has 1000 classes. So researchers, what they have done is they have tried out different things, different activation function, different layers and everything, so that you don't have to go and use and understand the whole thing. So we will now be studying about these different case studies of CNN. That means these different models and architectures that have experimentally been proven and scientifically also that they perform better than other architectures. Like I can also make any architecture, right? But that is not the thing. So scientists have actually proven, experimentally shown through different experiments and everything, that okay, this is the best way how you can build an architecture. This is one architecture, this is the other architecture, these are some of the best architectures. Okay, this is how we should increase the layers, this is how the number of kernels we should be using and stuff like that. So hence we will be studying about these case studies. Now these are very important because most of the time when you will be working with classification problems, you will come across these. So it is very important to understand the architecture and know it and learn it, I mean. So this is the basic architecture. We are talking about the very first architecture. This is the ALexNet architecture. So this is the ALexNet. It was in 2012. This was first it came out, and we will be discussing about this. So this is a very big deep architecture, and it was like very big when it came out in 2012. It took like 5-6 days to complete the training. It had 60 million parameters, and even though it sounds like a lot, I mean at that time, believe me, it was huge. So that is why it took 5 to 6 days to train it on two, I guess 3-4 GPUs, and it had 60 million parameters, so it's a lot. Okay, so first we have the image. So the actual thing is, when you have an input image, it is an RGB image. For this challenge you have RGB images. So ALexNet gets hold of RGB images, alright, and the images are of size 256 cross 256. But you might have noticed something here. This here takes the input as 227 cross 227. So why is that? Okay, so even though the input is 256 cross 256, the model takes 227 cross 227. These are random crops that have been done from 256 cross 256. Alright, so let's suppose you have an image here and it is of 256 cross 256. So one time I might take this part of it, and this might be 227 cross 227. The next time I might take let's say this part of a random image, and now this is 227 cross 227. So all the images have been randomly cropped. Okay, so why that is done, we'll come back to that also later on, but yeah, let's get back here first. So you need to make sure that whenever you input, the actual input data should be of this size, 227 cross 227 cross 3 being RGB channels. Okay, so this will be, first of all, ALexNet has 5 convolution layers and 3 fully connected layers, FC. FC means fully connected layers, alright. So let's start with that. Okay, so you have this input of 227 cross 227 cross 3. If you will read the paper of ALexNet, it has been given that the input is 224 cross 224. So why is there a 227 cross 227 here? Okay, the reason why this is because they have written 224 cross 224, but actually this is a mistake. If we look into their calculations and the way that they have done is, this should actually be 227 cross 227. Hence we will be taking this into consideration, 227 cross 227. So the first thing that happens is we have to decrease the size, increase the number of kernels and everything. So we will be doing convolution with 11 cross 11 filters. Now even though it is written as 11 cross 11, each filter is 11 cross 11 cross 3. Okay, 3 being again standing for the RGB channels. If you remember, you have the red channel of the image convolved with the red of the filter. Then you have the green of the image with the convolved with the green of the filter, and so on, and then you add the final thing with the bias and you get the final convolution for 3D. If you remember, we discussed over that. Okay, so now what we will do is we will understand the whole thing. So we have 11 cross 11 as the convolution, cross 3 obviously, and this is where it goes and becomes interesting. It has 96 kernels. So from the image, what that means is, from the image we are extracting 96 feature maps of the image. So again, some might be edges, one feature might be an edge, one might be a corner, one might be, I don't know, an inverse of an image or anything. So you can get a lot of things. So now here is the calculation to actually get the size that will be happening. If you remember, what was the formula exactly? The formula was n minus k plus 2p by s plus 1, right? So here that is what is happening. So we have 227 minus 11 divided by 4 plus 1, because we do not have any padding here. So that means when we will be writing the whole code for this, we will have to keep padding equal to valid. Okay, now back here. So 227 minus 11 by 4 plus 1 gives 55. Hence we will be having 55 cross 55, and I said the depth is equal to the number of convolution kernels that we will be using. So 96 kernels. So this is our output that we have gotten from convolution, right? So here we have the whole thing. Next, what will happen is we will pass this through max pooling. So now why max pooling? Again, let's get back to the question, max pooling. So max pooling helps in decreasing the dimensions without actually making loose of any important data. So it helps in decreasing of dimensions. So that is why we use max pooling. Okay, so we will do a max pooling of 3 cross 3 and stride is 2. So again we have the formula of the whole thing. And what does this come out to be? 55 minus 3 by 2 plus 1, 27. So 27 cross 27, and the depth remains the same. So we have the number of feature maps as the same, but now this size has decreased because we did max pooling, right? Okay, so now that the max pooling is done, if you remember, let's go back again. We had max pooling of something like this sort. So if you want just one pixel out of this whole thing, so we will take the maximum of all these 4 and we'll use that as a pixel. So that was the whole thing about max pooling. So one thing that you need to know is, after convolution, what happens is there is also something known as ReLU that takes place. You might have remembered these are activation functions that is happening. So it is not just convolution that is happening here. After this, it is passed through a ReLU function, and then we are getting the whole thing. Okay, so we have max pooling, then again we have a second convolution. Here the convolution is 5 cross 5 and we have a padding of 2, and this has 256 kernels. So now the feature map is 256 and 27 cross 27. Okay, and the padding is 2, so hence we'll have to calculate again. Now this time what will happen is this will become 27 minus kernel size is 5 plus 2 cross 2, which is equal to 4, divided by the stride is equal to, I guess, okay, the stride is 1. Okay, remember, whenever the stride is not given, it is actually 1 plus 1. So this comes out to be what? 27. So that means the dimensions are the same. And also one more thing to remember is, in this ALexNet, you might have noticed, but I'm still saying, the kernel size, the kernel or the filter width is equal to the height. So these are basically square kind of kernels, except for the channels or the depth, which is equal to the number of channels of the image. So yeah, this is 5 cross 5, and so you can see this is a square one. Obviously this is into cross 3, and we get the whole thing, 27 plus 27, and this is 256. Okay, next again we'll do max pooling here, and this 27 will be reduced to 13 plus 13 and 256. Alright, next we have another convolution. Now this time the convolution layers are one after the other, 3. Okay, so we are not having any max pooling here, they are just 3 straight up convolutions. So we have a 3 cross 3 convolution with a padding of 1 and 384 kernels this time. Okay, so one thing that you have to remember in these networks is, what they have found is, you have one image with a depth of 3, and the whole basic thing about this is making this height and width smaller, and its depth you need to keep increasing. That is basically what they have found out works the best. So that is what is happening in this whole thing. You have an image and you are just making it smaller and smaller and smaller, at the same time increasing its depth. Cool. Okay, so you have a convolution, 3 cross 3, padding equal to 1 and 384 kernels. Same formula you need to apply, and once you do that, this whole thing comes out to be a 13 cross 13 and 384, because 384 is the number of kernels. Okay, followed by another convolution and another convolution, and finally you have a max pooling, and this gives you a 6 cross 6 cross 256 as our output. Now here is where we end the convolutions. Now what will happen is, we will flatten this whole thing out to form a FC layer, that is a fully connected layer. So this will be flattened out to 9216, and once that has been flattened out, it will be connected to fully connected layers, one after the other. First is 4096, the next is again 4096, and the final one is a 1000 softmax layer. So the reason why it is 1000 is because you have a 1000 classes to find out. So this is a softmax layer. So what softmax will do is, basically it will give the probability that it belongs to a particular class, the image belongs to a particular class. So that is the whole thing about ALexNet here. Okay, now let us talk about what made ALexNet a good network. Let me clear this. So first of all, ALexNet had ReLU architecture, or ReLU activation, sorry. So what ReLU does is, basically this is a very good activation layer, because if you might have remembered, it has something of like this of a structure, and ReLU has helped in better convergence, easier convergence actually, faster convergence. So that is why ALexNet has ReLU, which has helped it a lot. Now these are the reasons why ALexNet actually works. Number one is ReLU activation. Okay. Number two, one of the things that I forgot to mention obviously is that after convolution it passes through a ReLU activation, right? I mentioned that. But after that it also passes through a local normalization. We don't have to get into the details of the local normalization. The reason being is, local normalization, it was there, but once it was removed, even then we saw that there was not a lot of improvement in the normalization. So hence local normalization was later removed from ALexNet, and this was the structure that was kept. So we don't have to study about or learn about local normalization as such. Alright, but I wanted to mention this. Okay, this is not the whole thing. Actually we also have local normalization here. So this is local normalization is basically in the first 3 convolution layers. Okay, Now let us talk about other reasons. So we had ReLU activation as number 1. Number 2 we had was dropout. So why exactly did we need dropout? First of all, let us understand one of the problems with ALexNet. Like I mentioned, it has 60 million parameters. This brings us to our problem of overfitting, like I mentioned. So we need some regularizers to help prevent overfitting. Hence we had this concept of dropout. Now the final thing that I wanted to mention obviously is, you might remember that I said we have 256 cross 256 as our image, right? But then we are using only 227 cross 227. Although the paper mentions 224 cross 224, but remember it is actually 227 cross 227, because only through using this data are we getting the actual values as is intended by the paper. So I think 224 cross 224 is a misprint, and it took me a lot of time actually to figure it out, because when I was going and when I was learning this myself, I had a big problem understanding, okay, why is in some blogs written as 224, in the other it's 227. I went through the paper itself and it made no sense because the calculations were not coming out to be right. So then I later assumed, okay, so it's 227 cross 227, but it is written 224 cross 224. It might be a problem, a misprint. Okay, so we have 256 cross 256. We used to do random crops. So one of the things that we can use to avoid overfitting is increasing our data. This is done through something which is known as a data augmentation. Now this is very much used when it comes to problems with computer vision. So CNN is obviously a part of computer vision. So this is basically used in computer vision. How does this actually help and what is actually done? So augmentation basically means increasing the size of the data set, data set size increase by random means. Like you have an image. So let's suppose you have a bee here. So a basic data augmentation will be like this. A random flip maybe, a random upside down, a random crop can happen, or you can tilt the image by some angle or something like that. So you have a dog in this manner and then you tilt it, so it is now in this manner. So you can have dogs in both manner obviously, but what happens is this increases our data set by a huge margin actually. So when you increase the data, it decreases your chances of overfitting, right? So we have talked about 3 reasons why ALexNet is actually very important and why it has helped top and actually improve our data set a lot. So one of the things was ReLU. What ReLU did is helped in better convergence or faster convergence. Next, what it did is dropout. So one of the problems that we had when I was saying was, when you increase the number of layers, you have the problem of overfitting. To prevent this problem, ReLU used dropout. ALexNet used dropout a lot. So this was one of the ways to regularize. Then the last thing that it used was random augmentations. So augmentations were random crops, you can say, or you can say flips, or mirror images, or tilting of an image. I mean, a lot of things that you can do with it, right? So these were some data augmentation techniques. Okay, so just a recap, we have ALexNet. Now it is very important to understand and learn the architecture, because in interviews they usually ask about the architecture. You have to describe it. So in that case you should actually know what is happening. Okay, so the whole architecture is basically, you have an input of 227 cross 227 cross 3. You have 5 convolution layers and 3 fully connected layers. You need an output of 1000 with a softmax layer which is fully connected, and you have 2 other fully connected layers of 4096. The whole task about this is, first you have an 11 cross 11 kernel size. Then this keeps on decreasing to 3 cross 3, 5 cross 5, and so 11 cross 11 then decreases to 5 cross 5 and 3 cross 3. After the first convolution you have a max pooling, after second convolution you have max pooling, then the third, fourth and fifth convolutions are one after the other, and final you have one more max pooling. That is followed by a flattening out and two fully connected layers followed by the final output layer. So this is the whole basic structure of ALexNet, and I know this is a lot, and obviously you might learn this and remember this now, but you might forget it later on, and this totally happens to me obviously, so I'm not gonna say, but just refresh this memory when you are going for an interview. Keep this in your mind because this will actually be required a lot. Okay, so that's it. Thank you and keep learning.